Good evening, everybody. I am going to take us through a couple redox reactions here. This is coming from the Chapter 4 handout, Chem 111. I'm going to take us through B and C in this redox reaction section. So I'll just start, and I promise if you can do these, you can do the ones in the exam. So B, I have a formula here, and I know it's a redox reaction. And first thing I'm going to do is assign charges to each individual atom, okay? We need to do that first because I got to know what's being reduced and what's being oxidized. Kind of helps me determine where I'm going to put my electrons and what I need to isolate from, outside of spectator ions to balance it efficiently and correctly. So putting charges on these, copper is going to be 0 because it's by itself. Then looking at HNO3 here, start with the O, the oxygen. That's typically a -2 charge, which is cool. And total, it'll be -6, right? Because there's 3 of them in that molecule. Hydrogen, I'll hit that one next. It's typically a +1 charge, right? There are cases where it can be -1. That's fine. But in this case, it's going to be plus. So it's +1. And right now, I'm sitting at an overall charge on the molecule of -5. Well, if the only thing I have left is nitrogen, I'm going to guess that that is going to be the +5 that's going to balance this out and make it neutral. Skipping on over to the product side, I have copper nitrate, okay? Don't let this part trip you up or anything. It does all balance out in the end. When I'm giving oxidation charges to something like copper nitrate, I do want to start with what's familiar, okay? So start with the oxygen. I'm going to put that -2 charge on there. And I'm going to say that because there's 3 of these oxygen molecules inside of, 3 of these oxygens inside of the nitrate molecule, I am giving it a charge of -6. And you say, oh, what about the 2 that's sitting there? What do you mean? There's 2 nitrate molecules. That's okay. I'm just doing it. We're doing it by 1 molecule of nitrate. And this equation will get balanced after it is all combined back together. And we will deal with that 2 subscript outside of the parentheses. Don't worry. So looking over here, I'm going to say that I know that nitrate is going to have an overall charge of -1, right? And so if my 3 oxygens are giving me -6, I can assume that nitrogen in this case has not changed, and it will be a +5 for an overall charge here of -1. And that makes sense. So looking at copper now, I ask myself, well, what is copper, right? Consider this -1 charge on the nitrate. I'm going to multiply by 2, right? Things balance out, multiply by 2. Which makes it a total -2 charge, and in that case my copper will have to be a +2 because there's only 1 of them. Going on to nitrogen oxide over here, NO. Oxygen, again, I'm just given a -2 charge. There's only 1 nitrogen here, so a +2 is fitting. And then last thing is water. Oxygen will be that -2. And H2, those are just going to be +1, right? There's 2 of them. That balances out. So now that I have my charges, I need to determine what the heck I'm balancing here, right? What's being oxidized, what's being reduced. So I'm looking through, and I see that copper, right? Copper has changed its charge. It looks like it went from a 0 to a +2. That would be oxidation. So I'm going to come over here, and we've got our oxidation is going to go there. Reduction will go below it. So let's look at everything else here. Looking for something that's reduced. First thing that draws me in is these nitrates. I have several NO pairs all over this equation. I look at this nitrate on HNO3, okay? Actually, nitric acid. And it has all the same charges, right? +5 and -2 as the nitrates on copper nitrate. So I'm not really too concerned. But when I move over one to this this lovely nitrogen oxide here, I see that the nitrogen itself, it has changed from what it was on the reactant side. So I have a +2, where over here in HNO3, the nitrogen had a charge of +5. So I'm going to assume that that is what is being reduced. Okay, going from a lovely +5 charge to a +2 charge. And now I'm just going to write these equations. So we are going to kind of separate them out. I don't need the spectator ions in this case. So writing the copper formula will be easy, our oxidation formula. It's just going to be copper, right? Coming from right here, reactant side. And I'm going to leave some space, but I will draw, we'll draw the arrow. Copper yields this copper, Cu, and we're going to put its charge on it. So Cu2 plus, and that is the full formula. Looking at the reduced species, and you know what, I'm going to move this down a little bit. Looking at the reduced species, it's the nitrogen that's doing the work here. But because nitrogen is closely attached to oxygen in both of these things, we're going to treat that as the molecule that we're balancing. But what I can get rid of is this hydrogen. I don't need to add that in, okay? So how I would write this is I would just take the ionic form of nitrate, which would be NO3 minus, has a minus charge, and then it's turning into NO, which has a neutral charge. So it gained, sorry, not gained, it lost an electron. Fantastic. Now the question is, how the heck do I balance these? And again, I'm going to move this over a little so I have more room. How do I balance them? Well, first up's first. I'm always going to start by looking at the just the non-oxygen, non-hydrogen elements in each of these. I have to balance them. Look at the oxidation formula. Copper and copper, are those balanced? Absolutely. I can even go to the reduced formula. Are the nitrogens balanced? Yes, they are. I don't have to add any coefficients. Now I look at the charge in our oxidation formula, copper to copper 2 plus. I need to make it neutral, right? I need to describe what's happening. So in order for copper to produce copper 2 plus, there has to be spare electrons hanging around, right? I am going to have 2 spare electrons. Incredible. And that's it, right? I balanced the charges. That's literally the whole point. Just make it neutral for these lovely problems. But then the reduced species, slightly different. Okay, so I look at NO3 minus, and if I'm going to something neutral, that means my goal is to make the left side of the equation here neutral. Okay, we always want to match our reduced charge. And so NO3 minus, I know nitrogen is balanced, but my oxygens are off. What you can do is if I see 3 oxygen over here, I'm going to balance that out by adding 3 waters. That provides our oxygen. Now, okay, I have added 3 waters. Yeah. Okay, now I have added our 3 waters, gave me 3 more oxygen. Oh, you know what's tripping me up? I only need 2. So sorry guys, that's a blip on me. I only need 2 oxygen because one's coming from nitrogen oxide, the other 2 are coming from water. That's my bad. I kept looking at the answer key. I was like, no way, I'm tripping. Okay, I've balanced oxygen, but now I have hydrogens, right? So because I have 2 hydrogens, 4 from H2O, I'm going to add 4 on the other side. Balancing, okay? Balancing. Unfortunately, when I add these 4 hydrogens, that makes it a +3 charge. And I can't have that, right? I'm at a +3 on the reactant side right now. I need to get to 0. So I am going to add 3 electrons. Period. Period. Love that. So these are now officially balanced. Both of them. They're both neutral. And that's the goal. It's not always the goal, like we'll see in the next one, but in this case, we wanted both of them to be neutral. So we have what we need. Problem now is, I need to be able to cancel out my number of electrons. So I have to multiply. I'm going to multiply them both using their lowest common multiple. And for 2 and 3, that would be 6. So I'm going to multiply this entire equation. So copper to copper 2 plus is going to be multiplied by 3. And then nitrate to nitrogen oxide will be multiplied by 2. That way, our electrons will all equal 6. So I'm just going to, you know what I might do? I might just put the coefficients, put the coefficients in front of them already. That would be easier. Ooh. So when I do that, let me pick a pretty color. Now I have 3 copper. I have 3 copper 2 plus, and I have 6 electrons. Amazing. Going down to the next one, I have 2 nitrate. I have 8 hydrogen. I have 6 electrons, exactly what I wanted. 2 nitrogen oxide, and then 4 water. So they all have their coefficients now. We're on a roll. What I'm going to do next is I'm just going to combine all the reactants and products of these 2 equations. Okay? So combine. Next step. Hooray. I've got 3 copper plus 2 nitrate plus 8 hydrogen plus 6 electrons. That will yield 3 copper 2 plus 2 nitrogen oxide plus 4 H2O, and let's not forget our 6 electrons. So now is the time when we cancel. I want to cancel the electrons. I don't need them anymore. They're here literally just to be canceled. And now I am left with kind of the skeleton of the core equation. The last step we have to do is simply rewrite it, but with the spectator ions that we left out previously, right? So I'm looking at it and I'm like, all right, I got a lot going on. I know copper is going to come down directly as is, 3Cu, because it's alone. There's just 3 of them now. I look at the other reactant, okay? The only other reactant that we were given, I'm directing you back towards the top, was nitric acid, HNO3. So I'm going to assume here that my NO3 and my hydrogen are going to combine to make HNO3. Fantastic. The question always is, how many? And we'll fill that in later, right? Because I got 8 hydrogen, two nitrate molecules, so we'll see. We'll keep going, right? I'm going to move on to the products. So I've got copper and nitrate that need to form together. So I do have this 3Cu2 plus sitting here. So I'm going to say 3 copper, and I'm just going to attach, right? And how about I write these spectator ions in green? NO3, 2. Amazing. So that stays as is. It looks like I have 2 nitrogen oxide, so we'll bring that down. And then I also have 4 water. Amazing. Now I gotta ask, what the heck do I put in front of my HNO3? Kind of a hard question. So where I would start is, I would say it's either going to be a 2 or it's going to be an 8. And I can try both. But I like to count maybe one of the elements on the other side of the equation just so I don't waste time, okay? So looking over here, let's just count how many hydrogens we have on the product side, right? Oof, I got 8. So I think that literally solves it for me. 8, period. And yeah, that's literally it. You could also verify that by balancing the oxygens. That'll make a big difference. There should be 24 on each side. But other than that little balancing step at the end, we're done. Look at that. I know that took a significant amount of time. I'm over explaining, but this means that we're confident that we kind of know what's up and we can move